All right, in this video, we're going to be looking at a couple sections in chapter 7. One of them deals with, one of the things I'm going to talk about is the polar form. And I want to go ahead and talk about the polar form of three things, just regular old points, complex numbers, and vectors. And then the other topic I want to look at is De Moivre's theorem and how it can be used to make finding powers and roots and multiplying numbers a little bit easier. All right, so let me start just with this idea of the polar form and get you to see right off the bat the connection between what it looks like for points, for complex numbers, and for vectors. Okay, so if you have a point, just think about it like some point AB. Okay, you can come over here and, of course, plot it like normal in a rectangular coordinate system. -1 is your x coordinate, square root of 3 is your y coordinate. That's about 1.7, so that's why I located it where I did. All right, the polar form for a point would be r with an angle. R being the radius of a circle that would have that point on it. So like if I were to draw a circle and this were a point on the circle, what would be the radius? So it would be that right there is your r. Okay. And then theta would be the amount of rotation. So this rotation angle here. So those are the two things I need. And so we can use the information we already have. So the first thing you do is you drop that. Let me change it into red. So I want you to drop that perpendicular. Okay. And then think about this being square root of 3. This is -1 right here, to the left 1. And if you needed the radius, you already know how to do that. So you don't really need my help with that. To get the radius, you would just do the radius squared equals the square root of 3 squared plus the -1 squared. And so r would be the square root of square root of 3 squared, which is 3, and then -1 squared is 1. So that turns out to be equal to the square root of 4, which is 2. So we know r is 2. All right, now what you do to get your theta is tricky in one respect. You've got to make sure you get your angle to be representing the rotation, giving you the angle in this second quadrant. So the formula that you might notice and want to use just says that theta is going to equal tan inverse of y over x. So remember how the coordinates right there. Okay, the y over x. So that would be square root of 3 over -1. So that would be that tan inverse equals negative square root of 3. Now this is one that we could do just looking at the unit circle. All right, the thing is, if we were to do this on our calculator, we'd have to be careful because it would give us an angle in either the first or fourth quadrant. And since the tangent was negative, it's going to be giving us an angle in the fourth quadrant, and we really need an angle over here in the second quadrant. So basically, if I think about this, if I don't put the negative on the -1, and I just think about, look for do you have angles on the unit circle that wind up having a square root of 3 on them, the first one you see is going to be over on let me think of which way it's going to be. It's going to be up here, okay? And so have a unit circle handy. Some of the problems you can do without resorting to the calculator, so you'd use just a unit circle, and then others you can go to the calculator when the angles you're talking about aren't on the unit circle. I've got to find where I put my unit circle. Okay, so we can tell that that's going to be that the angle over here this angle would be pi over 3. That would have a tangent that's square root of 3. And then you can see on the unit circle, when you get over there, do you see how that has the tangent would have a tangent being negative square root of 3? So theta turns out to equal 2 pi over 3, doesn't it? So look at your unit circle for that, since it turned out to be something we could find on the unit circle. And notice that we need on the unit circle to be over in the second quadrant. So that's going to turn out to be 2 pi over 3. So then you put those two pieces together. So you have your r and you have the angle, and you just put them together. And so this would be written as 2 and then 2 pi over 3. So it's telling you the amount of the rotation and then what the length of that line segment from the origin to the point would be. And we will be going back and forth with that as I work through homework problems. All right, now with complex numbers, sometimes they're indicated using a Z. It's like you have an A and a B here. The A is the real part, and the B here is the imaginary part. And you can't graph these in a regular rectangular coordinate plane because of that imaginary part. Each of those, each of the axes on this first example, the Y and the X axes, those are both real number lines. All the locations on them are real numbers. So what we do is we make one axis real numbers and the other one for the imaginary numbers. And then when you think about the location of that point, you're basically going to plot the ordered pair. You're basically going to think about it just like we did before and plot that ordered pair. Okay. Now, you don't do all the work for all three things. Like you'll maybe have a complex number and try to put it in polar form. But we're going to make use of what we already found in our first case, in this example, okay, when you have a point. All right, so you just need to know what the form looks like. So the polar form of a complex number has the radius, and then it has cosine theta plus I sine theta, okay? And then if you didn't already do the problem, like we already did a lot of that information back in example 1, then you would have to go through that work to identify the radius and the angle. But since we already know that, this complex number right here, we can express it. We already have the information. The radius was 2, and then it was 2 pi over 3 for the angle. Make sure you have a parenthesis there, plus I sine 2 pi over 3. So there you have it, okay? Now, when you have complex numbers, the language changes a little bit. Like on the earlier problem, I called R just the radius of the circle. Well, down here, R is the absolute value of the complex number, but it's not found by just making the A and the B positive. It's actually the square root of A squared plus B squared, okay? And they will later use the term modulus for that, so I might as well introduce that here. So it's the absolute value of the complex numbers, really the modulus, but in reality, it's just this, okay? The distance from the origin to the point, okay, that represents that complex number. All right, and then your theta is found just like we did on the others. You have to watch out and adjust for the quadrant like we did, but you can use tangent to find it, but you need to adjust for the quadrant you need to be in, and then that's called the argument. Kind of like function language. The argument is the input, okay? All right, and then if we had something represented as a vector, if you had something represented as a vector, then you think of it a little differently. You think of it as a directed, I can't draw straight for some reason today. You think of it as a directed line segment. So let me get that drawn a little better, okay? So it's this line segment from the origin to that point. That's the vector, right? And then we use the A and the B on that, AI plus BJ. So like a complex number is A plus BI is the general form for that. And for a vector, it's AI plus BJ. And we use the letter V. If we could bold it, we could just write V. But since we can't, we put the little vector symbol on top. So if we have a vector, okay, and they give that to us, we basically can just think about it as a point, like -1 square root of 3. The A part, that right there, is the horizontal component of the vector. Okay, what you do in the X direction. And then this part is the vertical component, what you do in the Y direction. So it fits, it's very comparable to just plotting the point, -1 square root of 3. All right, and then the polar form for a vector is going to have a look very similar to the complex number. It's just that the r gets distributed and you throw the I and the j on there. So r cosine theta is the horizontal component. So you represent that by putting an I, and then r sine theta will be the vertical component, and that's the j. Okay. And so we already know the information. If we didn't, we would have calculated it. But earlier, remember how r turned out to be 2. Okay, and theta was 2 pi over 3, so I just need to fill those in. Okay, and then I have 2 sine 2 pi over 3 with a j. Okay, and that would be your vector expressed in polar form. And you would find the r and find the angle in the same way I did for just the point earlier. Now the language, like with complex numbers, changes a little bit. The r is called the magnitude of the vector, and you'll see these 2 lines written on it. The magnitude of the vector. But it's just like the absolute value of z, and it's just like the radius. It's basically just the Pythagorean theorem, the square root of a squared plus b squared. But that's the magnitude of the vector. And then the theta isn't called the argument, but it's found the same way. Okay, but it's called the direction angle. All right, so you just need to know the angle, and you need to know the r. Same thing here. You need to know the angle, and you need to know the r. All right, so let me go ahead and get to a new page, if I can get it to scroll down, and we'll do some examples that come off of the homework, and you'll see them on the 50 question assessment. All right, so let me find that. Okay, so let's look at a couple things. I think you'll be okay just plotting the point. So let's do one where you're actually having to convert. All right, so what if you had the point 4 and then 7 pi over 4, and these are the polar coordinates. And your job was to go the other way and figure out the regular rectangular coordinates. Okay. All right, so I think it helps to visualize this. All right, so you think about where is 7 pi over 4. So that means you want to think about breaking up pi here into 4 pieces so you can count your way around it. So that would be 1, 2, 3, 4, 5, 6. This is 7 pi over 4. All right, or since it is a point on the unit circle, you could look at that. So that's the angle. It's going to go all the way to here. So this is the angle, theta. And then 4 is how far out on that you're going to go. And so that's the location of it. So basically, we need to figure out what the XY coordinate would be. Okay. And so what you want to do is drop your vertical here. And basically what you need to do is figure out this horizontal component and this vertical component. Okay. Well, you know this is 4. And so what you need to do is just think about how this right here is the cosine related to cosine, and the vertical component is related to sine. And so when you try to get the x coordinate, you just need to do r cosine theta. And when you do the y coordinate, you do r sine theta. And it'll turn out to have the correct positive and negative on it, because you're using the actual angle that's in whatever quadrant it winds up in. So the SIGN will turn out to be the same. So basically all you got to do is 4 cosine of 7 pi over 4, and then you need to do 4 times sine of 7 pi over 4. right? And you can look at your unit circle and determine it from just the unit circle. So that's probably the best thing to do, because a lot of times they'll want the exact value. So go to 7 pi over 4, or think about how everything at these pi over 4 sections has square root of 2 over 2. Cosine is positive, sine would be negative. Multiply by 4 on each of those and simplify, and you wind up getting 2 square root of 2 and then negative 2 square root of 2. So the coordinates of that point, rectangular coordinates, would be 2 square root of 2, negative 2 square root of 2. Okay, so this was my problem number 4 from the homework. Okay. All right, let me do some more that just have you kind of working through these different forms. Okay, here's one. This is number 7 from the homework. Okay, so it gives me a vector, and it tells me the vector is 3i plus 3j. Looks like that. They did it bold. I have to do that little arrow on top. And then I'm supposed to, graph it, figure out where it would be located. And then I'm supposed to find the magnitude, just those two things. So locate it and find the magnitude. So 3 would be right here, basically. So I just think of it like the point 3 to graph it. And then they asked me to find the magnitude of it, okay, which is this, which is actually just going to be, if I were to drop that perpendicular, it would be what's the radius. What's what we used to call the radius of the circle, or the hypotenuse of that right triangle. So it would just be the square root of 3 squared plus 3 squared, which is the square root of 18, or 3 square root of 2. That's all that problem wanted. And they did want an exact answer, so you didn't want to be putting the decimal in there. Okay, so then there's a couple more problems like that. All right, let's think about, okay, here's one that goes the other way. It's a vector problem, but it goes the reverse of this. This is number 10. So on number 10, and this is still on the homework, but you might have something similar on the test, they give me that the magnitude of the vector equals 6, and that theta is 120 degrees. Okay. And so I've got to try to figure out on this one, they want me to figure out, write the vector in terms of I and j. That's kind of like the rectangular form, find the I and the j. All right, so let's think about this one. So what's going to happen is I'm going to be over here, 120. Okay, that's the 120. And then I'm going to have my vector has a magnitude of 6, means this is 6. And then I'm trying to get it written in terms of the horizontal and vertical components. So it's basically dropping that right here, okay, and figuring out what this is and what that is. Okay, so again, it's going to be close, very closely related to what we did earlier. For the horizontal component, I'm going to do the magnitude times the cosine. And for the vertical component, I'm going to do the magnitude times the sine of the given angle. Okay, and then I'll throw the j on this guy and the I on this one, and that'll be my vector once I get it simplified. Okay, all right, so we want to come in here, and it's exact answer using radicals. Put your answer in AI plus BJ form. Make sure you've rationalized denominators, all of that. So basically, you can look at your unit circle for 120, and you can see the cosine is going to be a negative 1/2. So we have 6 times negative 1/2 for the I part. And then we have 6 times square root of 3 over 2 for the j part. Then we simplify those. So this would be negative 3i, and then this would be plus 3 square root of 3j, because the 2 would divide into the 6 3 times. Okay? And that's how you would write it. And it's really telling us that that terminal point right there would be at -3, 3 square root of 3. It's telling us that this is going into the left 3 units and then going up 3 square root of 3. So making those connections can just help you make sense of things, okay? All right, so let's keep going. Let's try a complex number. All right, so here's one. This is number 11 on the homework. So what if I wanted to plot the complex number and then write it in polar form? So plot and write in polar form. That's what the directions said. This is number 11. All right, so the complex number it's given me is 4 minus 4 square root of 3i. Okay, so you think about the real and the imaginary axis. You think about this like the point 4, -4 square root of 3. Think about that real part and the imaginary part basically just being like an ordered pair. So the real part is 4, the imaginary part is 4 square root of 3. I'm going to see about what that is as a decimal. So I'm going to do 4 times the square root of 3. Turns out to be around 6.9. Okay, 6.92. So when I go out there, I'm going to be down almost to 7. All right, and that's the location for that complex number. All right, so for me to get it into polar form, what I'm looking for is to have the r and then to have cosine theta plus I sine theta. That's what I'm trying to get it written out like. So I know how to get the r. The r is going to be this right here. And so I want you to imagine again that right triangle dropping the perpendicular to the x-axis, always to the x-axis. This is 4. This is the -4 square root of 3. So we know how we're going to get the r. For r, we're just going to do the square root of 4 squared plus -4 square root of 3 squared. So that's 16. And then this you need to be careful if you haven't done this in a while. So that's -4 times -4, which is 16. Square root of 3 times square root of 3 is square root of 9. And that's going to be 16 plus 16 times 3. And so you get 16 plus 48, which is 64, isn't it? Oh, nice. So that turns out to equal 8. So the radius turned out to be 8. All right, so that means we know that first part. We know this part is 8. Now we just need to figure out the angle, and the angle we're trying to get is this angle right here. So for that, I'm going to use the fact that the angle is going to equal tan inverse, and it's going to be opposite over adjacent, so -4 square root of 3 divided by 4. Okay. And then I want to think about what that is when I simplify it inside there, because that turns out to be, negative square root of 3. Now I'm supposed to be getting exact answers, so you really don't want to just go type that in on your calculator. You want to look at the unit circle. Since that's square root of 3, you know that's going to be the value of tangent when the y coordinate is square root of 3 over 2 and the x coordinate is 1/2. And you need to be in the fourth quadrant. So you see how it's 5 pi over 3? So I know that's 5 pi over 3. So now that I know that, I can put those two pieces of information together. And in polar form, I'm going to have 8 and then cosine 5 pi over 3 plus I sine 5 pi over 3. And you don't distribute the 8. You leave it like that when you write it. Okay. All right, so you'll have some problems like that. Sometimes they'll want you, if you are able to do exact answers and use the unit circle, you do. Sometimes you'll have to do like a decimal form. Okay. All right, let's do one with the complex number going the other way. Okay, that one's pretty nice. I think people mess up more than anything on their basic algebra on this. So sometimes they'll give it to you in polar form. So here's one in polar form. Okay. And what they're asking me to do is to put that in a plus bi form. So they want me to change it so it just looks like this. And that's called the rectangular coordinates or rectangular form. So when I do that, basically all I think is if I distributed the 4, I'd have that. And you know, that 4 doesn't cancel that denominator because this is function, the cosine of 9 pi over 4. So you go to your unit circle and you get your 9 pi over 4 on the unit circle. When you think about that, that's going all the way back around. That would be coterminal. That's the same location as pi over 4, isn't it? Because it went all the way around to 8 pi over 4 and then went pi over 4 past that. So you're actually in the first quadrant at pi over 4. So you can really just think of it as a pi over 4. So when you do, you just got to work out those two things. So you know that the sine and cosine of pi over 4 turns out to be square root of 2 over 2. And you have a 4 out in front of that one. And you simplify. And you get 2 square root of 2 plus 2 square root of 2 with an I. Now, when you type that in, you know how back with quadratics, we always sandwich the I in between the 2 and the square root of 2? That's technically what I want to do, just so you don't mess up how you write it. Just make sure your square root stops before you write the letter I. Okay. All right, so that's like working a little bit with polar form when you have complex numbers, and then just a little bit when you had a vector, and then in the beginning when you had something in polar form and you're trying to change it into rectangular coordinates. But it's all related to that right triangle that we draw. And when we draw the right triangle, we always draw the perpendicular to the x-axis. And then you can think about kind of the connection between all of these things. All right, so I'm going to go ahead and stop that.